Hey everyone. So this is the first section of chapter 5. So we are going to be working on finding the area under a curve using something called Riemann sums. We're going to do this in class, the 10-minute timed multiple choice practice. Okay. So I don't think you guys have learned summations unless you learned it in maybe an engineering class or something. So a summation is where you add up a bunch of numbers, right? A summation. So, for example, in this first one, what you do is we just plug in 1, right? It says n equals 1. So first we're going to do 2 times 1 minus 3, and we get negative 1. Then we're going to plug in 2. 2 times 2 minus 3, which is 1. Then we're going to plug in 3. 2 times 3 minus 3. 6 minus 3 is 3, and then we're going to plug in 4. Now we know to stop because of the number at the top, right? N is where we start, and we stop at 5, or it's 5. We stop at 4, so that's 5, and then we add them all up, so we get 8. So our final answer, the summation of 2n minus 3 from 1 to 4 is 8, and it's always integer numbers, right? So pause and try the next one. So we plug in 0, n equals 0, I get 1, n equals 1, I get 2, n equals 3 is 10, n equals 4, 16, 17, n equals 5 is 26. So then I add those up. Let's see, I get 20, 30, 56. So my final answer is 56, right? So a summation, it's really, you're going to see this in some definitions, is the idea of adding a bunch of things up, like a list of numbers up, is basically what a summation is. Okay. Approximate the area A of the region enclosed by the graph f of x equals 1/2 x plus 3, the x-axis, and the lines x equals 2 and x equals 4. Now, students every single year are like, oh, well, let's just break it up into a rectangle and a triangle. Okay, that's not allowed. So the process that we're going to be doing here is we're going to be making an actual rectangle, right? So either the rectangle could look like this. There's a rectangle that, because this is an estimate. We're not finding the actual area, we're just estimating it. So I could have this area, or I can have this area, right? Another thing that we're going to be doing is we could have this rectangle where it's like in between. So those are our 3 choices as of right now. Okay, so let's try using the left. This is called a left endpoint. So I'm taking the height of the rectangle from the left side, right? So the area of this rectangle is, if I plug in 2 into the function, we get 4, and the width of the rectangle is 2, so my area is 8, right? So that's a left rectangle. We also could do a right rectangle. So again, the height is, the base is 2, right? 2 to 4 is 2. If I plug in 4, I get 5. So the area of my rectangle this time is 10. So the left endpoint was an underestimate at 8. A right endpoint is an overestimate with a 10. All right. So how can we find the area more accurately? So here's that graph, the same picture. So instead of doing those big rectangles, what else could we do? Again, you're not allowed to make any triangles. So let's say, what if I cut it in half, right? And I had these 2 rectangles, right? So then I could have my left be like this, and there's not as much, we're not going to underestimate as much, right? This would be 1 times 4 and 1 times 4.5, it looks like. So 4.5, 4.5. So now we're at 8.5. Could we make it even more accurate? We could add in more rectangles, right? I could erase these. And what if I put in every 0.5 or 0.25 or something? Right? So look at, if I made all these rectangles, the underestimate and overestimate is going to get smaller and smaller. All right, so that's the idea here to find the area under a curve. And again, this one, because it's a line, we could find the exact area, but we're not going to be doing just a line, right? We're going to be doing curves. Okay, when we find the area under the curve between the lines x equals a and x equals b, we make some assumptions. F has to be continuous, and f is non-negative on the closed interval. So we are above the x-axis, right? We partition the interval into non-overlapping subintervals. Each interval is the same length. So when I make my rectangles, right, when I have my curve, right, and I make my little rectangles, what they're saying is these distances are the same. So if this is a 2, then this is a 2, then this is a 2. So we want our rectangles to be the same width. Now that's not always going to be the case, but it makes things easier. Okay, so here is the kind of the formula why I showed you a summation. So notice this is our what we call our delta x. That's our distance between each of the x's, and then f of c1, f of c2. So the function is the height, right? So what we're doing is we're adding up the areas of all these little rectangles under the curve to estimate that area, and that's where that summation comes from, because we're adding up a bunch of those areas that are next to each other. So all of these are all your delta x's, okay? These are all delta x. That's the distance between each little rectangle, and then we just plug in the height of the rectangle. But we have to decide, are we going to use a left or a right? Okay, approximate the area under the curve of the graph y equals x squared from 0 to 10 by using left sums. All right, so we have our parabola. We're going from 0 to 10, right? 5 subintervals. So what are we going up by if we have 5 intervals? 2's, right? 2, 4, 6, 8. And then I'm going to draw my heights in. So these are my rectangles. Approximate the area by left. So now that's important. We're using left. So we're going to take the height from the left side. So starting at 0. So notice my first rectangle isn't even a rectangle. It's just a line. At 2 from the left. 4 from the left. 6 from the left. And 8 from the left. So these are my rectangles. So 1, 2, 3, 4, and then 5. So the area of my first rectangle, right, is 2 times 0, right? The width times the height, plus 2 times, what's the height here at 2? Well, if you plug 2 into x squared, you get 4. And now we're going to plug in 4, right? I plugged in 0 first. Now I'm plugging in 2. Now I'm plugging in 4. So that's 16. Now I'm plugging in 6. 36. And then finally 8. 64. So notice there is an easier way to do this. There's a 2 everywhere. So what I do is usually the width for all of them, and then 0 squared plus 4 squared plus, sorry, that was 2 squared plus 4 squared and so on. All right. Yeah, so 2 squared, 4 squared, 6 squared, and 8 squared. And so we're just going to use that. We can plug it in the calculator or use our brains. Let's see, 36, 64, so it's 120. So 2 times 120. So our estimate is 240. And it's an underestimate, right? We have a lot of gaps in that graph, right? So there's all these gaps in here, right? So now pause and do the other side. Or sorry, pause and do 10 intervals. So what would it be with 10 intervals? So we're going to add in all the middle ones, right? So we have, now what's the width if we're adding in all of them? If we're going from 0 to 10, and we have 10 intervals, 1, 2, 3, 4, 5, 6. That's a terrible picture, right? So now the width is 1, right? And then I need to figure out all my y values. Again, we're starting from the left, so we're starting at the left interval. So we're starting at 0. So 0 squared, 1 squared, 2 squared, 3 squared, and so on. And so you notice why we have that summation, because doing this is super annoying and gets really tedious really fast. Now make sure you stop at 9, right? We have 10 rectangles and we're starting with 0. So that's, if we went to 10, that would be 11 rectangles. So pay attention to that, whether it's left or right. So let's see, 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64 plus 81 equals. All right, I got 285. So before it was an underestimate. This is less of an underestimate because they're smaller, right? So we're probably a little bit closer. And we're still an underestimate. So the actual answer will be higher than that. All right, there's my graph I didn't actually use. All right. Estimate the area under the curve using left endpoints and right endpoints. So this is straight from your book. So pause the video and use this picture and try this on your own. So from the left, I'm starting at 1 and I'm making my left rectangle, left rectangle, left rectangle. Okay, so I have a width of 1, and then my heights are 7 over 2, 5 over 2, and 2. So let's see, that's 12 over 2, so 6 plus 2 is 8. So the answer is 8. And then we're going to do a right interval. So then I start at the right. I'm going to start at 4. So this is going to be way less, right? It's an underestimate. My width is still 1, and I always start at the right. So at 4, my y value is a half. And then 3 is 2. And then 5 over 2. So let's see, we get 6 over 2 plus 2. So for this one, we get 5. So the actual answer will be somewhere between 5 and 8. I mean, that's a really big range, so it's not super accurate, but it works. All right, last one. Approximate the area A under the graph of the function f from A to to B. I typed the word B. That's funny. From 4 to 6. For n equals 4 and n equals 6 subintervals 0 to pi. Use lower sums, rectangles that lie below the graph, by using upper sums where we are above the graph. So this is the graph of sine, right? So it's only from 0 to pi. So they want us to do, there's two problems here. There's our n equals 4. So let's do n equals 4 over here. And then we're going to do n equals 6. So I need 4 subintervals. So here's pi. So we got 1, 2, 3, 4. So what are each of these things? What is this point then? Pi over 4, pi over 2, 3 pi over 4. Right. So that's what we're using there. Now this one's a little different though. It says by using lower sums, rectangles that lie below the graph. So my rectangle here would be right there. And then my next rectangle would be from the left. But then as I get to the right side of this would be my lower. And then this would be my lower. So this is a little different. It's not strictly left, strictly right. They just want the underestimate. They don't want to overestimate at all. So I have my two like zeros, right? So 0, 0. And then what's this distance? That distance is pi over 4. And then what's the height, right? What is the distance going up and down, right? Well, sine of pi over 4 is root 2 over 2. So we have root 2 over 2 for this guy and root 2 over 2 for this guy. So root 2 over 2 plus root 2 over 2. So our estimate is pi over 4 times root 2. So pi root 2 all over 4. It's a little weird, but whatever. Okay, so now let's do underneath here. Let's do our overestimate. So let's still keep with the n equals 4. What would be our overestimate? So now here is my overestimate for this guy. And then we have this one, and then this one. So we still have our pi over 4 for each of them, but what are the heights of each of my rectangles? So the height here for this one is pi over 4, sine of pi over 4, which is root 2 over 2. What is the height here? Well, that's just sine of pi over 2. What's sine of pi over 2? That's 1. And then 1 again. And then root 2 over 2 again. So we get pi over 4 times root 2 plus 2. So our answer is super weird. I'm just going to leave it like that. I don't even care. All right. So that was 4 rectangles. Now we're going to do 6 rectangles. This one's a little harder. Well, just because there's more, really. Right? All right, so here's my pi. Okay, so now we're doing 6 rectangles. So that's pi over 6. What comes next? 2 pi over 6, which is pi over 3. 3 pi over 6, which is pi over 2. 4 pi over 6. 4 pi, 2 pi over 3. And 5 pi over 6. And I ran out of room again. All right. So pi over 6, 3 pi over 6, pi over 2, 2 pi over 3, 5 pi over 6, and pi over 6. All right. So underestimate, we got that dude, this guy, this guy, this guy, this guy. Sorry if you're offended that they're all guys, but whatever. Okay, so this time the width of all of my rectangles is pi over 6. And if you want to do, pi over 6 times 0 plus pi over 6 times whatever, go for it. I don't like doing that. It's too much work in my opinion. So the first rectangle is just a 0. Right? And then the next one, this first line. So what is sine of pi over 6? Well, pi over 6 is 30 degrees. Sine of 30 degrees is a half. And then I got my root 3 over 2. Another root 3 over 2 because of the underestimate. 2 pi over 3. Root 3 over 2. And then another 1/2. All right. So we end up with pi over 6. 1, 2, 3, 4, 5. That's only 5. What did I forget? 1, 2, 3, 4, 5. Pi over 6, 1/2. Root 3 over 2. Root 3 over 2. Oh, 0. I didn't include the other 0. Okay, so there's my 6. So we get 1 plus root 3. So that's that answer. So that's my underestimate. And then my overestimate, there's that rectangle, this rectangle, that rectangle, this rectangle. All right. So again, we got our pi over 6. And then this first one, our height is pi over 6 again, which was 1/2, plus pi over 3. That's 60 degrees, which is root 3 over 2. And then these two are both 1, right? That's at pi over 2, so 1 plus 1. Here, we're back at root 3 over 2. And back at a half. Right, so I have 1, 2, 3, 4, 5, 6. And I write them all out so I can count, make sure I'm doing this right. So for this one, we get pi over 6 times, let's see, 1, 2, 3, plus root 3. And that is it. Right, so this is a difference of 2, right? 1 plus root 3 and then 3 plus root 3. All right, that is it for area under the curve. It's a little tedious, but it's not very difficult, right? The notation is weird, but it's not overly hard at all. All right, that is definitely, page 390, yeah. So take a picture of either page 390 or bring your textbook to class so we can practice this for the first half of class. This homework 64 is not due on Friday. We're going to be working on it in class on Friday, all right? So those are the problems we're going to do in class for the first half. All right, have a great day. Bye.